All right, so now we're going to become masters of sketching things by hand. So here I've listed a bunch of things that we know how to do and to find, and you can find this at the beginning of section 3.6. So I'm going to color code these, and I'm going to just make up a function that has certain attributes, and show you why that's good. Okay, so I'm just going to say x and y intercepts, right? So let's just color code that in blue, and let's say we know that there's a y-intercept here, and an x-intercept here, and an x-intercept here. Okay, so we're kind of getting an idea of some kind of a curve like this. Okay, symmetry, you know, if you're graphing a parabola or something that has a certain kind of symmetry, that can be useful. We'll say it doesn't apply to this function. Domain and range, that would be, well, kind of goes along with vertical asymptotes, continuity, right, holes and vertical asymptotes, things like that. Let's say that we know there's a vertical asymptote right here. Okay. All right, so we're getting an idea of some things here. Differentiability, that kind of goes along with domain and range and holes and that kind of thing. If there's any place where the derivative is undefined, it's probably because the function is undefined, but perhaps if you found that there was a undefined, there'd be like a cusp or something, but we'll kind of discount that. Relative extrema, okay? Let's say that we know there is some kind of an extrema. Here, maybe we'll move to orange so we can see it. Some kind of like an extrema there. Right, and let's say we know it's a max. Like we can figure that out from the first derivative test or the second derivative test. So let's say we know there's a max there, and let's say we know there's a minimum right here, right at like 2 1/3 or something. All right, so we know that, and let's say we know there's a minimum like right here. Okay, we found our local extrema. Okay, concavity. Let's choose purple for that. Concavity, let's say we know that it changes concavity here. Like, I mean, really knowing the concavity is really knowing about points of inflection, right? We are finding places where it changes concavity. The concavity informs us of the relative extrema, of course, but we'll lump these together with like points of inflection. And then let's say we know that it switches concavity here. All right. Let's say that we know, here, let's go back to extreme. Let's say we know that there's some stuff going on here, that it's kind of a maximum there as well. Okay, local maximum. And if we know vertical asymptotes, then we should know what's happening near the vertical asymptotes. So, well, no, that's all right. Well, let's just say that we know the points of inflection in the concavity, and let's say that we know if it switches concavity here and here, it must be the same concavity throughout here. So we'll say it's concave down. We should get the purple back. So let's say we know it's concave down here, and then we know that it's concave up on this interval. I want to move that actually. Guys down. I'm just going to put them on the axis here. So I know that it's concave down on this interval. I know it's concave up on this interval. Let's say I know that on this entire interval, let's say, I'm trying to imagine a function here. Let's say that we know it is going to change concavity here, and here it's concave down, and here it is concave up. Okay, these are useful things. And we know that it changes concavity, say, here. Okay, and from here to there, it's concave up. And look at all the information we have about this thing. And here we know it's concave down. Horizontal asymptote, let's just give the horizontal asymptote, make it easy. Just say there's a horizontal asymptote on the y-axis, right? Now that's a section we've covered before. We grabbed it from chapter 3 and used it earlier. Limits at infinity, right? End behavior. Okay, and infinite limits at infinity. Well, that would be since this is a limit at infinity or an end behavior, this is just a different kind of end behavior, right? We could just lump these together with end behavior. Okay, I guess that B has two vertical things. All right, so we know all of these things about the function, so let's see if we can sketch this curve out. All right, it's got a maximum here, right? No surprise that it's concave down. It's got a maximum here, all right? It's got a minimum here. It's got a minimum here, so obviously it's concave up, right? That's matching up with what I know. Of course, I would have known that was a minimum because I checked the concavity with the second derivative test, right? I know that it goes through here. I know that it's going to change to concave down here at this point of inflection, so I try and keep it concave up, and then switch to concave down, and stay concave down till we get here. Try to switch to... So we're trying to make it look like it's a concave down. Comes up through here. You know, if I was doing this work, I would know, like, hey, I must have missed an x-intercept or something, because if it's concave up, right, and there's a vertical asymptote here, then it would, you know, if it were to not cross the x-axis, it would have to go back down this way, which, since it's only concave up on this interval, it must just keep going up like this, right? Concave up. Okay, so you come over here, it's still concave up, right? We know that here. And now it's concave down. But then it's forever approaching 0. Okay, so that's what that looks like. Over here we have a maximum, it's concave down, then it's concave up, and it's approaching the horizontal asymptote. Alright, and then it's just concave down forever. It never is concave up. It never is going to switch back to going up like this, right? It's be an interval where the derivative is increasing and increasing. It's just the derivative as we move from left to right is decreasing, getting smaller. It's big positive here. It's not as positive. It's very small. It's 0, and now it's negative, more negative. Okay. And then it switches to concave up, and now it's negative, but it's getting less negative, less negative, less negative, approaching a 0 slope. Okay? So see how all those pieces of information, though I didn't really know much about the function's values exactly, except for the extrema. Oh, I forgot to go through that maximum. Why didn't you say something? I did not go through the maximum as I was supposed to. Just went through that y-intercept. Okay, so come back, we go concave down, go through the maximum, through the y-intercept. There we go, now it's better. So we did find the y values of the minimum, maximum, minimum, maximum, the y values of the y-intercept. Okay, we found the x-intercepts. Should have found an x-intercept there as well, obviously. But you get the idea. I was making it up on the fly, so I missed a few things. But if we had all that information, we could plot all those points and the intervals where it's concave up and down. We can graph a really decent graph without having to plug a bunch of numbers into the function, right? So I'm going to take all of these guys, and I'm going to turn them into a list that I can move around. Okay, so I can just pull it out of the way, and we can bring it back up and talk about it. So let's move on to our first example. All right, so what to do first? That's what we have to decide. So we grab our list here. How about x and y-intercepts? How do I find those things? Well, first y-intercept, so easy, right? That's when x is 0. So if x is 0, 0, 0, 0, I have a y of 5/3. So the y-intercept is 0, 5/3. Alright, so now I can grab this guy right here, do 5/3. That's going to be right about there. Okay. And then we can move on to x-intercepts. That's a little bit trickier. But if you notice, this function is a quadratic, if you look at it this way. 3x squared minus 6x squared to the first power plus 5/3. There's my a, b, and c. Okay, so I can use the quadratic formula, x squared equals, so I'm solving for x squared, not x. Okay, so then I'm going to have x squared is equal to these things, and then I'll have to take the square roots of those things, right? So I will pause the recording. I'll do that all real quick and show you the end result. All right, so you can see how I just used a quadratic formula. Boom, 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 boom. What I got to here, I just split it up to the two solutions, the plus the square root and minus the square root. Notice 36 minus 20 is 16. The square root of 16 is 4. So we get plus or minus 4, right? So 6 plus 4 is 10 over 6. That's 5/3. X squared also could be 1/3. So we take the square root of both sides, and we get x equals plus or minus the square root of 5/3. Right, so that's going to be a positive square root of 5/3 and a negative square root of 5/3. It's going to be over here somewhere. And x also equals the square root of 1/3. Okay? So, how big are those numbers? Well, they're about approximately plus or minus 1.29, plus or minus 0.58. Okay, so plus 1.29, that's going to be, I'm going to make this a little darker blue. So 1.29 positive, 1.29 in the negative, 0.58 in the positive, 0.58 in the negative. There's my x-intercepts, okay? Pretty simple. I'm just going to go ahead and erase this work because I know that you could rewind it if you wanted to review that. We don't need it anymore. Like, we have those values. So we take that away. So what do we do next? Let's see. X and y intercepts, symmetry, domain and range. You know, we're going to want to find any holes or vertical asymptotes. There aren't any with this function, so done with that. Differentiability, relative extrema. Let's find some relative extrema with the second derivative test. Okay. So we know that what we need to do is find the derivative in the second derivative. So y prime equals 12x to the third minus 12x plus 0. Y double prime equals 36x minus 12. Okay, what do we do with that? Well, remember, extrema are going to only live where the derivative is 0 or undefined. No undefined for the derivative here, so we'll find the zeros. Okay, so we'll set 12x cubed minus 12x equal to 0. 12x gets factored out. We got x squared minus 1 equals 0. So x equals 0 or x equals plus or minus 1. So those are places where we may have extrema. Okay. Now, I'm going to do you a favor here, give you a heads up. We are going to also want to find the zeros of the second derivative, okay? And so my heads up is in reference to this little chart that we have here. Here, let me just do something real quick here. To the front, okay. Oh, that's no good. Let's try and just kind of get it out of the way here. So we've got this little chart, right? And we're going to write on it all the stuff that we find. And one of those things that we're going to find is going to be the zeros of the second derivative. So we found the zeros of the first derivative. That's great. But also, when we go to write down the x values and the intervals that are of interest to us, we're going to, if we just do the zeros of the derivative right now, we may not leave ourselves room for the zeros of the second derivative. So before we fill that out, let's just find the zeros of the second derivative too, before we start filling out that thing. So the second derivative, 36x minus 12 equals 0. So we add 12 to both sides. X is going to be equal to 1/3. That is the place where we may see a point of inflection, and we probably will see a point of inflection. Let's see. You may have noticed that I caught a mistake. What was my mistake? You probably caught it a long time ago. It's 36x squared, so it is x squared equals 1/3. So x squared, or x, equals plus or minus the square root of 1/3. Remember that those right here and there, those were also some x-intercepts. Okay, so these double as possible points of inflection. Okay. And for our first derivative, we found zeros at 0, at 1, and -1. So, I don't know, you may want to just kind of put little marks there. It's not something I normally do, but just indicating to you that those are places where we're probably going to find some extrema. Okay, so now we pull our chart up, knowing what the zeros of the first and second derivative are. And let's just go from -infinity to infinity, writing down all the things that are important to us, okay? So what's farthest to the left? We got -1 there. Let's see. Yeah, so we'll go to -1. So x is less than -1, x equals -1, x is between -1, and what? What's next? Negative square root of 1/3. Negative square root of 1/3. Okay, and x is equal to 1/3. Let's try and make that look a little better. X is equal to negative square root of 1/3. And x is between negative square root of 1/3. Glad I made this so big so I could write easily on it. And let's see, 0. Okay, 0 would be next. Alright, and x equals 0, and x is between 0 and the positive square root of 1/3. X is equal to the square root of 1/3. X is, I know this is riveting, 1/3. And I shouldn't have written 0, I should have written x. And 1, and x equals 1, and x is greater than 1. So going off to positive infinity. Okay, so let's look. Why do we care about x is equal to -1? Because it was a 0 of the derivative, so we put a 0 there. Why do we care about the square root of, or the negative square root of 1/3? Because that's possibly a point of inflection because the second derivative is 0. Okay, why do we care about 0? Because the derivative is 0 there. 1/3, square root of 1/3, excuse me, is a possible point of inflection, right? We would love to write point of inflection right here. So x equals 1. That is going to be where the derivative was 0. We hope to write maximum or minimum here. Okay, so we're finding lots of useful information. So now we are done. Well, we're done with all of this stuff. We found the zeros, and that's what we care about. We're done with finding the zeros. We still want to use the derivative because we have to look at it, and the second derivative, look at its positiveness and negativeness. Okay, so first of all, let's look at the intervals of concavity. Okay, we only really care about what's going on here and here and here, right? You can only switch concavity here and here, so we only need to be concerned about what kind of concavity we see here and here and here. Luckily, at these values are in between those two x values, right, for the possible points of inflection. So if we test this guy, we can find its concavity, and we'll know whether it's concave up and down on this interval in between these possible points of inflection. So let's test 0 where? In the second derivative, okay? Let's put 0 in there, get -12, so what do we care? It's a negative. Okay, that together with the derivative of 0, it's concave down, we have a 0 slope, so we have a maximum. Okay, let's test -1 in the second derivative. -1, we're going to square -1, that's going to be positive 1. 36 minus 12 is going to be positive. It's concave up. It's got a 0 slope. That is a minimum. Well, it switches from concave up to concave down, so that is a point of inflection. Okay, and we'll just test this 1, but that's going to be the same as positive 1, or sorry, -1, so that's going to be concave up, so we're going to get also a minimum here, and we're going to have a point of inflection at this guy right here. Okay, so pretty cool stuff. So we have a minimum, we have a point of inflection, we have a maximum, point of inflection, and a minimum. We know the, what's the end behavior of this function here? Like, what's f of x going to do as we let x what is f of x going to do as x gets very large? Well, we know something about fourth degree polynomials. It's an even, its leading coefficient is positive, so it's going to go off to infinity, right? It could have a horizontal asymptote, it could have gone to negative infinity, no, it's not doing that, it's going off to positive infinity. Okay, so we go to negative, we put the negative in there, it's evens, and this is a positive here, so also as x goes to, sorry, this was negative infinity, positive infinity. In either case, it goes to infinity. The y values go to infinity. So now what we need to do is to actually know where those points are, those maxima, minima, points of inflection. Where are they, right? So we actually have to know the value of f of x to do that, okay? So where is this minimum? Well, I have to plug -1 into this function, right? -1. Well, that's just going to be, well, that's positive, and that's going to be positive, so that's negative, so -3 plus 5/3. -3 plus 5/3, that's -9/3, so -4/3. I'm going to double check myself. Alright, I just want to make sure I was right there. Okay, so we have a point of inflection. Where is that point of inflection? We need to put in the negative square root of 1/3. Okay, so however you want to do it, where am I going to put this? I'm going to put this over here, so 3 times negative square root of 1/3. I would like some exact values, right? That's why I'm going to plug it in my calculator and figuring out what the decimal is. So minus 6 times negative square root of 1/3 squared plus 5/3. So we get 1/3 times the square root of 1/3 times the square root of 1/3 is 1/3, and then we're going to do 1/3 times 1/3. So we're going to get 3 times, it's going to be positive, of course, 1/9 minus 6 times positive 1/3 plus 5/3. So we're going to get 1/3 minus, let's call it 6/3 because we're going to have common denominators here, plus 5/3. Okay, so we have 5, 6, you know what, it's kind of a silly thing I did there, because we found it was an x-intercept. We already knew that. We already knew it was an x-intercept. And you can see it was going to come out to be 0. Duh. Okay. So, that's accomplished. And I realize I just put the wrong thing there. It should be here, where x is equal to 1/3. Alright, so we have where the minimum is, where the point of inflection is, where this point of inflection is, where this point of inflection is. Now we need to know just where is this minimum, where is this maximum, okay? That's where x is 0, so easy to find that maximum. Where x is 0, well, that's the y-intercept, so that was lucky. So what did that turn out to be? 5/3, right, 5/3. Next, x is 1. What happens if x is 1? The same thing as when x is -1. We're going to get -4/3. Okay, it turns out this is a nice symmetrical function. Could I have told that, should I have been able to tell that from the function? Sure, you could have, but I think it wastes more space in our brain trying to remember which functions are symmetrical. Like, what are the tricks for finding that they're symmetrical, and what are the tricks for knowing that they're not symmetrical? So it's kind of a silly thing. So here we go. -4/3, so -1, comma 4/3. Alright, that is a minimum value. So -1, -4/3. That's a minimum value. I could just even write a little note for myself if I can't keep track of that mentally. 1 comma -4/3 also is a minimum. I know that it is concave down on this interval, okay, so I bet I could sketch something that's concave down that goes through that y-intercept, and which is also a maximum, which we found. And we can come down here, right? We're trying to draw something that's concave up. I should have had a graph that went from -5 to 5. It's concave, it just keeps going concave up. It just never stops being concave up. It keeps going to infinity. We know as x goes to infinity, y goes to infinity. Here we have concave up, a minimum. Goes to that x-intercept. Alright, we've switched concavity to up, so if it just keeps going up, there there's our function. Pretty decent approximation of the function. So there we go, pretty simple. Let's go on to the next one. Okay, this guy right here, we want to find some x-intercepts, y-intercepts. I'm not going to worry too much about symmetry. Let's see, domain and range. Yeah, we're going to find some vertical asymptotes there. Continuity, vertical asymptotes, already said that. Relative extrema, if there's any extrema. Concavity is good, right? Most of this stuff down here, and I think x and y intercepts are the most useful thing. So, let's just go ahead and graph these x-intercepts. Okay. So my x-intercepts and my y-intercepts. Okay, let's find the y-intercepts first. Put a 0 in there. 0, 0. Well, that's 0 in the numerator, so our y-intercept is going to be 0. Okay, y-intercept is 0. Clearly an x-intercept of 0. Are the other any other x-intercepts? Well, that's where y is equal to 0. And of course, we're going to multiply both sides by the denominator. We get x equals 0. That's the only x-intercept. So we're done with x and y-intercepts. And this time we were smart enough to keep track of it over here. Alright, so we found x and y-intercepts. Check. Symmetry, I don't know. When it comes to vertical asymptotes, let's see if there's any vertical asymptotes. Is that going to happen? Well, the vertical asymptotes will happen wherever the denominator is 0, right? Wherever any badness for this function happens. Well, it's not a square root, so no badness that way. It's not a natural log, no badness that way. Badness in a fraction is dividing by 0. Okay, x squared plus 1 equals 0. X squared equals negative 1. Already I can see this is not going to be possible for x squared to be negative 1 unless it's a complex number, which it can't be because we're graphing real numbers. So no vertical asymptotes. Not applicable. Okay, so we just keep going through our list here. Vertical asymptote, differential, relative extrema. Let's do that. Let's find the derivative in the second derivative. First derivative, of course we always do that in dark purple. Y prime equals, trying to think if we can use any tricks here. Now we're just going to have to go ahead and use the quotient rule. So, low d high, that's 1, okay, minus high d low, and we're over the square of what's below. Okay, so that is going to be x squared minus 2x squared is negative x squared plus 1. And, oh, that was the square, right? What's below? Over x squared plus 1 squared. Okay, so what do we care about the derivative? We care if it's equal to 0, which means just the numerator needs to be equal to 0. X squared plus 1 equals 0. So x is going to be equal to plus or minus 1. Okay, so that's going to be something we want to note on our little table, right? It keeps track of all that info. Let's see. We've got our y-intercept, x-intercept. Now we're going to take the second derivative. Right, this is the derivative of the derivative. Here is the derivative. So we're going to take the derivative of that. See if there's any concavity switches, right? So we have low, which is a lot of stuff. D high, that's negative 2x minus high. That's negative x squared plus 1. D low, oh man. So low, d high, d low. So we got 2 times x squared plus 1 times 2x over the square of what's below, which is x squared plus 1 to the 4th, because we're squaring something that's squared. Okay, so we want to know when is this guy 0, right? So we want to know any possible points of inflection. So let's set it equal to 0, and at the same time, let's multiply this guy out. So we're going to get x to the 4th plus 2x squared plus 1 minus times negative 2x. Gets multiplied by negative 2x. Minus, okay, negative x squared plus 1 times 2x squared, actually, forget, this is actually at 4x, right, if we multiply these together, so we get 4x to the third plus 4x. And we only need to be concerned if the numerator is equal to 0, not the denominator. So we're just working with the numerator here. 0 equals, let's see what to simplify. Negative 2x distributed in here. We get negative 2x to the fifth minus 4x cubed minus 2x minus, we're going to just multiply these together, negative 4x to the fifth. And let's see, we're going to get third, so this is a third, this will be a third. So 4x to the third minus 4x to the third, so no x to the thirds there. And then just in x terms, so plus 4x. We're getting there, negative 2x to the fifth. Let's see. Actually, let's put everything together. We got a negative 2x to the fifth plus a 4x to the fifth. So we have a 2x to the fifth minus 4x cubed. We got a negative 2x minus 4x. We got minus 6x. Okay. We keep going. We're going to factor out a 2x. And we get x to the fourth minus 2x squared minus 3x. Okay, so that's 2x times, let's see, can we factor this as a quadratic, right? Recognize it as a quadratic. Oh no, it's not a quadratic because we shouldn't even have that last x there. So now it is a quadratic. So we factor it as a quadratic where we have an x squared, we have negative 3, positive 1. Check it yourself. It comes out right. So x equals 0, right? 2x equals 0, x equals 0. X squared plus 1 equals 0, impossible. X squared minus 3 equals 0. X equals plus or minus the square root of 3. So what are those? Those are possible points of inflection, because that's the second derivative. So we get out our table. Right. And make sure it doesn't carry away that point there. Alright, so what x values are we interested in? Here, I'm going to paint this like light yellow, because that's fun, in case you didn't know. Okay, so what x values are of interest to us? Alright, we got plus or minus 1, we've got 0, we've got plus and minus the square root of 3. Okay, so as we come from x is less, so as x goes to infinity, or as x is less than the smallest x value, which would be negative square root of 3, right? So negative square root of 3. What's happening there? What's the concavity? You know what's happening? What is happening when x is equal to the negative square root of 3? Okay, now x is between two values. It's between the negative square root of 3 and what? What's next? Negative 1. And then x is negative 1. What's happening there? Is there a point of inflection, extrema, something? And then it's between negative 1 and 0, then it is 0, then it's between 0 and positive 1, and then it is 1, and then it's between 1 and the square root of 3, and then it is the square root of 3, and then it is greater than the square root of 3, right? It just keeps going. Okay, so let's see. Negative square root of 3, what's going on there? Double prime is 0. What's going on at negative 1? We've got a extrema there, possibly. X is 0, we've got a possible point of inflection. X is 1, we've got hopefully an extrema of some kind, and then another possible point of inflection. Okay, this looks like a pretty interesting function. Let's see. So let's try and find some extrema. Let's see if that's happening. -1. We plug that into the second derivative. You know, it's a kind of a useful thing that we found out now. Now that we did all that work, all of this simplifies down to that. So let's just get rid of that. The numerator now is much cleaner. Does this take a lot of time? Sometimes it does. But, wait, what else are you going to do? This is the funnest thing you could be doing right now. So, we're going to multiply, we're going to plug in, what are we going to plug in? A -1. So, let's just kind of keep track of this. -1, that's -2 times 1 plus 1 is 2. That's another 1 minus 3 is -2, so we got a +8. So what do we care about that? It's positive, right? It's a positive for that. So it's a positive second derivative. It's concave up. It's got a 0 slope. That, what do we have there? We have a minimum. Of course, we're going to have to find the y value of the minimum in just a second. But let's keep going. Let's try with +1. Probably some sign changes in here. +1, so that's a +2, all the same. So now we have a -8, so that's a negative concavity. So this is a maximum. Okay. What's going on here? Oh, look at that. We switched from positive to negative, so this is a point of inflection. It is a point of inflection. I already said that. So let's look. Is this a point of inflection? Well, we're just going to look somewhere in the, somewhere less than -√3. What's less? What's less than the -√3? -2. All right, let's plug -2 in there. See what's going on. -2. Okay, so -2 times -2, that's -4. -2 squared, that's 4 plus 1, that's 5. -2 squared 4 minus 2, that's 1. So it's a -20, so it's a negative second derivative. So it switches from concave down to concave up, so it is indeed a point of inflection. Let's try this again with +2. What's going to happen when we do +2? Nothing's going to be different except this will be a +4. So it is a positive second derivative. It is concave up, so this also is a point of inflection. So we know that these are all things that we want to actually find, so we have to find their y values, okay? So now that we have done everything we could possibly want to do with first and second derivative, let's clear this out of here. All right. If we need to revisit it, we can Control-Z all the way back, or you can rewind the video. Just make sure to keep watching as I erase all of this stuff. Almost done erasing. Okay. Now we're going back to the original function. We're going to plug in what? -√3 to find the y value of this point of inflection, and then on and on and on. -√3. -√3 over -√3 squared is going to be 3 plus 1. That equals -√3 over 4. -√3 over 4. We're going to want to find an approximation for that, but that's exactly what it is. Okay, what's going to happen when we put in positive square root of 3? Well, it's going to be positive. That's still be positive. So it'll be positive √3 over 4. So that was helpful. Where is this point of inflection? It's when we plug a 0 in here. Well, that's going to be at 0. That point of inflection is actually going to be at the x/y intercept. Keep it going. -1 over -1 squared. So it's -1 over 2. So it's -1/2. And we put in +1. That's going to be +1/2. All right, we are ready. Okay, we're ready to go. Ready to graph all this stuff. Let's get an approximation for the square root of 3 over 4. That did not take. Wow. We good now? 0.43. So we're at negative 0.3, positive 0.43. What's going on here? Point of inflection, 0.43, so negative root 3, which we know is like 1.29 from the last problem, and negative 0.43 is somewhere in there. Alright, that's a point of inflection. We'll do them in colors here in a second. We'll do another point of inflection at 0, 0. Okay. Another point of inflection at root 3, so that's like 1.29 and positive root 3 over 4, so that's 0.43. So we're right around in there now. Okay, so these are points of inflection. Let's color code this. Actually, so what's going on in this interval? Are we looking at, let's see, there's a point of inflection, point of inflection, point of inflection. So right here, is it concave up or is it concave down? It is concave up. Right here, it's concave down. And here, for all of eternity, it switches back to concave up. Okay. Okay, I can see this starting to take shape here, and this is concave down, right on this interval to the left of negative square root of 3. Okay, so that's the concavity. Now we move on to the extrema, the minimum. This minimum is at negative 1, negative 1/2, negative 1, negative 1/2, which is just a little bit lower than root 3 over 4. And this other guy here, this maximum is at, well, yeah, it should be down here. 1, comma 1/2, 1, comma 1/2, which is just barely above the point of inflection. That kind of makes sense. Alright, let's graph this whole thing. Maybe an orange. Okay, so it's concave down here, and it goes up to a maximum. Okay, and it comes to this point of inflection, switches. Oh, what's happening as we go on to infinity, right? Should I go this way? Should I approach 0? Well, as it goes to infinity, we know something about rational functions, and that if I let this guy go to infinity, this guy to infinity, this will be so much bigger than that, that the whole function pretty much goes to 0. So they have this horizontal asymptote at 0, right? So we go to concave up, and we approach 0 forever. Oh, this I really should have. I don't know what I was thinking. Maybe I can zoom in a little bit. That's better. Okay. Then we are concave up here, and we are hitting our minimum. We're going through this point of inflection, so we're going to switch back to concave down, and we're going to approach the horizontal asymptote. Let's just say forever. Okay, approaching that horizontal asymptote. So there we go. We got our points of inflection, maximum, minimum, horizontal asymptote. Doing great. Okay, and on to the next slide. This will be my last example. Alright, let's bring this up here. X and y intercepts. Okay, so we're going to let x be 0, so we can find a y-intercept really easily. X is going to be 0, that's going to be 0. Alright, so we know that automatically have an x-intercept. Let's erase those, try this again. X-intercept at 0, also y-intercept at 0, because it happens to be at the origin. Are there more x-intercepts? Well, let's find out. If x cubed equals 0, then we have an x-intercept, right? Because we'll have a 0 in the numerator. Take the cube root of both sides, you still just get x is 0, so there's no more than that. We found all the x-intercepts. Now let's move on to vertical asymptotes and horizontal asymptotes. Okay, vertical asymptotes. First, where will vertical asymptotes happen? It will happen when the denominator is 0, right? It happens whenever bad things happen in this function. This function only will be bad when we divide by 0. So x squared minus 4 equals 0. That happens at plus or minus 2. So plus or minus 2, plus or minus 2, look how good that looks. So at positive 2 we have a vertical asymptote, and at -2, we have a vertical asymptote. And we don't even have to really worry about like what's going to happen as we approach the vertical asymptote. You know what's going to tell us about that is at the very least concavity, right? If it's concave up, it will go up. If it's concave down, it will go down like this, right? So we don't have to worry about that. So let's not. Next, like I said, let's talk about horizontal asymptotes, or I'll just say other, okay? Let's look, as x goes to infinity, let's pull up our little chart here, okay? Or as x goes to negative infinity, and let's leave lots of room, as x goes to a positive infinity, what's going to happen to our function? Well, as x goes to negative infinity, what's going to happen here? Well, we're going to get a negative up here. We're going to get a positive down here as x goes very, very large, right? And so this function is going to go to infinity. Sorry, negative infinity, because there's going to be a negative up here, right? Because this number is going to be bigger than this number, much, much bigger, x times bigger than this number here, and so we essentially will have x cubed over x squared. Okay, what happens as we go to positive infinity? Well, same thing except for we go to positive infinity in the y direction. Okay. Now, think about it, like, even though it goes to infinity, this function will act more and more and more like this. More and more and more, just like there's an x, right? Try yourself, put in 1,000,000, right? Put in 1,000,000, and this whole thing, I bet you what you'll come out with something is really close to 1,000,000. Because what's happening, we're putting 1,000,000, and we're cubing it, 1,000,000, and we're squaring it. If this -4 wasn't there, 1,000,000 cubed over 1,000,000 squared would be just 1,000,000, right? It's going to be slightly off, slightly more than 1,000,000, because we are taking 4 away from 1,000,000 squared. But as x gets to be more and more huge, -4 is going to be more and more insignificant, okay? So we're going to get a function that's acting more and more like this. What does this function look like? It looks like a line with a slope of 1 and a y-intercept of 0. Okay, so that's interesting. Let me show you in a different way. Let's do, pardon me, some long division polynomials to show you that it's going to look more and more like this. It's basically going to be f of x equals x plus something that gets more and more tiny as x gets larger. Okay, so we do x cubed. You always are going to do this if you have a difference between the numerator and denominator of 1 degree, if the numerator is 1 degree higher. So you're going to divide that by x squared minus 4. Okay, so if you need a refresher of long division, let me know. But what we need to do is say x squared times what is x cubed, right? Because this times this needs to be this. So this times this needs to be x cubed. Well, that's going to be x, just x. X times x squared is x cubed. But x times -4 is -4x. Okay. Well, there's a 0x here, right? So what we subtract this, we find that that's a 4x. I cannot multiply x squared by something else to get 4x, right? So that's just my remainder. So I get 4x over x squared minus 4. And that's excuse me, this is x times, yeah. So we get a remainder of 4x over x squared minus 4. So that's that little piece right here, 4x over x squared minus 4. Sorry for writing it so tiny, but you can see how if x is 1,000,000, well, we're going to get 1,000,000 here, and then this is going to be so tiny that we're going to be 1,000,000 plus this tiny little thing, right? It's not going to be very much. That's the same conclusion we came to over here. So this function, as x gets to be bigger and bigger and bigger, is going to act more and more and more like it's just a line with a slope of 1 that goes through the x-intercept. So this is what we call our slant asymptote. Now, this slant asymptote, just like a horizontal asymptote, is irrelevant when x is like 0 or 1 or 2 or 3, but when x is 10 and 100 and 1,000 and 1,000,000, then we will be approaching that slant asymptote. Okay, so when we differ, when the numerator is 1 degree larger, we're going to find a slant asymptote. Okay, so moving along, we're going to need to find the derivative and the second derivative. Okay, first derivative, dark purple. We need a pen for this. I'll just do this while the video is paused so you don't have to watch me do it. Okay, so I'm going to admit to you that was an insane amount of work. You can see it here. You can recreate it yourself. I doubt that you will, and I wouldn't blame you. But what did we find out? Not much, so it makes it so much more satisfying. So we found for the first derivative that the first derivative is 0 at 0 and plus or minus the square root of 12. Okay, so negative square root of 12 is going to be our first x value that we care about. That's 2 root 2, 2 root 3, 2 root 3, whatever. And then between the negative square root of 12 and, what's 0? No, negative 2. Actually, here's what we're going to find out. The second derivative is 0 at negative 2. Is that really important? It might be a point of inflection, but remember we also found vertical asymptotes at plus or minus 2. So, while the numerator of the second derivative is 0, look, the denominator at the same time is also 0. Okay, so we get this weird thing happening where it's actually the second derivative is undefined also at plus or minus 2. So we did all that work to find out that plus and minus 2 not actually like usable, okay, for the second derivative. It's undefined. The second derivative is undefined at plus and minus 2, which of course makes sense because the original function is undefined at plus and minus 2. Okay. Next, so we are going to ignore that negative 2 because there's a vertical asymptote. We already know what's going on there. So we'll go to 0. Okay, to 0. And then what's next? X is 0. Right, we get a 0 slope there, maybe. Well, 0 slope, definitely. Maximum, minimum, maybe. And then between 0 and the positive square root of 12, then when x is the square root of 12, and then when x goes to infinity. So we can move all that stuff up here. Okay. And we found that slope asymptote for that. Okay. So we need to find out what's going on with the function at these points. Okay, so what's happening at the negative square root of 12, it is a slope of 0, also at the positive square root of 12, also at 0 we have a slope of 12. Alright, so we want to find out, are these maximum, minimum values? Let's find out. We want to use concavity, right? So, at the negative square root of 12, what's going on? Here it is, with the second derivative. Okay, I'm going to find out for you real quick. Alright, and now that we know that we have a concave down and concave up interval, at this point where the slope is 0, we know that this is a maximum. We know that this is a minimum. How about this guy right here? The slope is 0. What's the second derivative? Turns out it's also 0. Right? We did the work there. We took the second derivative. We set it equal to 0. We found all the solutions, and one of the solutions was 0. So at x equals 0, the second derivative is 0. So what do we conclude? Well, it just means the second derivative test is inconclusive. So how do we figure out if this is a maximum or a minimum, or neither? Well, we need to use the first derivative test. We look on the left and the right of 0, right, and between 0 and negative root 12 and 0 and positive root 12, somewhere in there, and see, do we go from a positive slope to a negative, or vice versa, or neither? Okay, so we go to the first derivative, is right here. Okay, we can look at this first derivative here. Let's go to negative 1. That'd be easy. Okay, so negative 1, that's actually going to be a positive 1 right there, and negative 1 squared, so that's going to be minus 12, and then a negative 1 minus 4. We're just trying to figure out if this is positive or negative, right? So this is negative. This is, well, it's squared, right? It's definitely going to be positive. So we have a negative over positive, so it's a negative slope. Okay, when we put in negative 1. And we put in positive 1, and we're still going to get a 1 minus a 12 over, it's going to be a positive again. It's going to be a positive 9. So we're going to get a negative over a positive again, so we're going to get a negative. So it is neither. It's neither a maximum or a minimum. It's just a place where we come down, we have a negative slopes, a 0 slope, and just keep on going with them negative slopes. Okay. Let's see, we have got everything we need. Let me just clear this up, and I'll bring you back. Alright, so we're all cleaned up, and we are looking at the stuff that we know. We have the slant asymptote, we have this x and / y intercept, we have vertical asymptotes at plus and minus 2. We have a maximum at negative root 12. And what is the value of that maximum? We need to plug in negative root 12 into that function. So I'll do that real quick. Okay, so I did that. Actually, quite a few things. So I was kind of laughing to myself. Anyway, we find that we have a negative 5.2 here, right? So that negative root 12, negative 5.2 is the location of a maximum. Here we have a minimum. Here we have a 0 for the second derivative, and it switches from concave down to concave up. So that must be a point of inflection. So we have a maximum, we have a minimum, we have a point of inflection, and it is not a maximum or a minimum, it's a point of inflection. And that makes sense. If it's going to be negative slopes to negative slopes, and it goes through a 0 slope, here we have negative slopes like that, right? Coming to a 0 slope, that's concave up, and concave down, we'll see that over here. Yeah, so let's plot those, that max and that min, and see where we are. So negative root 12 and negative 5.2. Negative root 12 is a little past 3, okay? And negative 5.2, 1, 2, 3, 4, 5.2, somewhere in that neighborhood, a little past 3, 2, 3, 4, 5.2, somewhere in there. Okay, that's the one on the left here is a maximum, the one on the right is a minimum. Here we have vertical asymptotes. What's going on? Is it concave up or down? Is there points of inflection over here? Looks like from, let's see. Oh, you know what? We should consider those vertical asymptotes, right? Because that's where the second derivative, the derivative, the function are all undefined, right? So that undefined could be a point of inflection. It could be a point where, or a place where the concavity changes. So we should look at the concavity at 1, okay? So if you want to, you can rewind back to that part of the video, look at the second derivative, plug in 1, plug in negative 1, okay, because we know what it is over here, but we don't know what it is to the right and the left of this guy here, okay? So jump back there. I'm going to do that myself. I'll be right back. Okay, so I found the concavity here and here, and I went ahead and moved everything around and included those values of negative 2 as we should have done. So we found that the concavity from negative 2 to 0 is concave up and then concave down to the right of that. All right, so it's concave up here. So it must look something like this. 0 slope here, 0 slope. Right? It's also a point of inflection, which when I switch to concave down, I can see that. Right? Concave down here. Then we have a minimum here, a minimum. And as I said, the bigger x gets, the more this function looks like a straight line with a slope of 1. And then it's still concave up. It doesn't change concavity, so it just keeps going up like that. It's all concave up on that entire interval, right? Once it gets past undefined, the second derivative is undefined, then it switches over to concave up. Okay, concave down over here makes our graph look like this. Alright, and we're done. Simple graph, a lot of math. So some of them can be really involved. Gotta watch out for those mistakes. My main mistake, I think, that cost the most trouble would be when I didn't include the -2 and 2 on our little chart here, because of course where the function is undefined, the slope is undefined, the second derivative is undefined, we're going to have a possible change of things, so especially concavity. So make sure when you find those vertical asymptotes you include them here. Otherwise we were good. We found all the things we needed to find. We found our maximum value here, minimum value here, x and y intercept, also a zero slope, also a point of inflection, lots of interesting things happening there. Vertical asymptote, slope asymptote, so there it all is, all there for you. So, raise your hand, let me know if you have any questions. Thanks for watching.